All right, Math 1 Bivariate Statistics Test Review. Now, this isn't necessarily all the problems. I'm going to put up another video where we kind of look using the calculator on some of the stuff, so that'll be another aspect of it. Okay, but this first stuff, we just want to know, describe the correlation based off the graph. So when we say describe, we're looking for these kind of terms. Okay, you have strong negative, you have weak negative, okay, which we can just SN, strong negative, WN, weak negative, no correlation, so that could just be none or no. Then we have weak positive, so WP, and weak negative, or not weak, strong positive. Okay, so if we look at number 1, okay, we're looking at how close together the points are aligned. Okay, it's going down as we look left to right, so it's definitely negative. Okay, and they're pretty close together. I'd probably call that a strong negative. Okay, if we look at number 2, this one's definitely a strong negative. Okay, this one's probably barely a strong negative. This one definitely is a strong negative. Number 3, it's a little more spread out. I'd probably call that a weak positive. Okay, number 4 would be a no correlation. Number 5, definitely a strong positive. 6, definitely a weak positive. Okay, so honestly, number 3 you could probably call a strong positive. It's probably more, not quite as strong as 5, but we'll say it's a strong positive. Okay, and there we go with those ones. Okay. All right, now what is most likely the correlational coefficient? So remember, the way it goes is like this. So we have our strong negative, our weak negative, our no correlation. So a strong one, the highest you can get is to a -1. That's like a perfect correlation. Okay, no correlation would be 0. So about at -0.5 is the difference of where we would say it goes from strong to weak. So let's look at all our negatives. So I'm looking at this negative, that's a negative, and that's a negative. Okay. So if I look at 12, it's definitely weaker than 7 and 8. 7 is pretty close to a line. It'd probably be like 0.9, -0.9. Whereas 8 maybe it'd be like -0.75. Okay. Maybe even -6. You could do -6, -7, maybe even -8, somewhere around in that range. 12 would definitely be more weak, so it'd probably be like -0.4. Okay, because it's still got a pretty good shape to it. All right. Now for positives, okay, we go weak positive, then strong positive, so it goes from 0 to about 0.5 is that difference between weak and strong, and then to +1. So anything between 0 and 0.5 would be a weak positive. Above 0.5 to 1 would be strong positive. So if I look at 11 and 10, 11 is like almost, it'd be like -0.98 or 0.98. Okay, really strong. Whereas 10 might be kind of like 8, would probably be why did I do a negative? It's positive 0.98. Whereas 10 would be more like a positive 0.7, maybe even 0.6. Very similar to 8 in the fact of how it's done. If we look at 9, that's definitely got a very weak correlation, so I'd probably just put 0. Maybe you could put like, looks like it's kind of going down, maybe like -0.1. Okay, but pretty weak. All right. Now identify if we should use a linear, a quadratic, or an exponential. Okay, linear, straight line, right? 14's definitely would need a linear line of best fit. Okay, 15 is definitely linear. Okay, if I look at 13 and 16, I've got that curvature, which would definitely be exponential. Okay, if something were to be quadratic, it would have to look like where it goes down and back up, kind of, or up and back down. That would be quadratic, so neither of those were quadratic. Alright, constructing a scatter plot. We can do this on the calculator, which we'll talk about in a different video. But if we're just doing it by hand, we just graph these points, right? X value of 0.2 up to 3, right about there. Then 0.2 up to 4, 0.2 to 4 again, so there was 2 that went right there. 0.3 to 4, 0.5 to 6, so pretty simple, right? And then 0.9 to 10. Look something like that. And there's my scatter plot. If I wanted to, I could say that's definitely a positive. Looks pretty strong, so probably a strong positive. It's probably like a 0.8 correlational coefficient. If I were to draw a line of best fit, probably something like that. But we'll get to that later. Okay, number 18. So I've got 3.6. That's going to be really small. It'll be like almost like a 0. 28 up to 11. That's not very high. 58 to 400. A little bit higher. 83. Now up to 7,000. Now we're making some headway. And 89 up to 16,000, and then 98 up to 46,000, so it'd be like up here. Okay, so there's our scatter plot. Okay, now this one is probably a weaker positive, but it's exponential, right? A line of best fit would definitely be an exponential, which they're harder to guess at what that correlational coefficient would be. That's where we definitely use the calculator to help us out with that. Okay, I'm looking at 19, so 10, 800, okay, 60, 500, right there, 70, 400, 80, 400, 80, 300, and 100 and 200. Okay, so there's our scatter plot, definitely another linear. Okay, probably like another negative 0.8, strong negative. Okay, line of best fit. Will look something along that lines, wouldn't it? Okay, then finally 20. 20 is at 140,000. Let's see, that would be 100, so 20 would be like right there. 190 to 11,000, right above there. 290, about 2,000, and then 480, 200, 720, and 930 are both very small. So again, we can see that kind of similar exponential aspect to it, can't we? So that'd be another exponential one. Pretty good for an exponential, but it would look something like that for the line of best fit. But all we needed to do was make the scatter plot, so that's all we cared about on this one. Alright, now we're going to take a look at how we kind of use these, aren't we? Alright, so this first one, they give us the table of values. They tell us it's going to be modeled by this equation, so we want to figure out what we can use this with, this line of best fit. So the y-intercept. The y-intercept would be that 1710. And what does it tell us? Well, it tells us where the year is 0, so at year 0, then the value of this investment would be 1,710. So that's basically how much she invested. Okay, that's kind of what we're looking at there. So then using the model, what would be the value of investment after 26 years? Okay, well, a few different ways we can do that. We can look at these and try to estimate at year 26, it would be over here, what would be our y value. Or we can take our equation and plug in 26 for x. And then just using a calculator, we figure that out. So notice here that we have an exponent. So I'd go 1710 times 1.12, and then I would raise that to the 26th, and it gives me this number. And because we're dealing with money, we round to the nearest hundredth. or it says round to your answer to the nearest dollar. So 32,558.52 would mean we round up to 59. So it'd be $32,559 is what the value of that initial investment would be. Okay. Then it says, according to the model, how long did it take the investment to be worth $6,700? Well, $6,700 is going to be somewhere in between here, isn't it? So if we look at about 6,700 on the graph, we kind of estimate over, and it looks pretty close to year 12. Okay, so I would say about year 12 is what I would do for that one. Just estimate it. All right, now a linear model, which can be a lot easier to deal with. So we have households consume much more electricity when the weather is warmer. So our input is the temperature. Our output is how much electricity a house used. We've got our scatter plot over here with our line of best fit with its equation. So what would this slope represent? The slope would be that 0.462. And slope is always a fraction. And the y value, in this case electricity, over the x value, in this case temperature. So what this slope tells us is that for every temperature increase of 1 in temperature means we use about 0.6462 kilowatts, I think that's what it is. Yeah, kilowatt hours of energy. So almost a half a kilowatt of energy is used for that per hour. Okay, and that's what the slope represents. Now what about the y-intercept? Y-intercept would be the 0.613. So, but it's when the value for temperature would be 0. So if the temperature is at 0 degrees, then we'd use about 6.13 kilowatt hours. Okay, that's kind of where it starts for our model. Now it says, according to this model, how much electricity would be consumed if the average daily temperature was 96 degrees Fahrenheit? Okay, so that's our input value, so I'd go y equals 0.462 times 96 for our degrees plus 613. And I'm just going to plug that into a calculator, right? So 0.462 times 96 plus 600, or 6.13. Type that in, and it says round to the nearest kilowatt hour, so that's 50.48. So we would just leave it at 50 kilowatt hours. Okay. Now part D says, well, what temperature would it need for us to use 39 kilowatt hours? Well, 39 is going to be right below that 74, so somewhere there. But because it's linear, we can actually use this equation. The difference is now we're given the y value instead of the x value. So then I just solve. So I subtract 6.13 from 39, giving me 32.87 equals 0.462x divided by 0.462. Oops, hit my arrow there. So that's 462. That'll tell me what the temperature would equal. So 32.87 divided by 0.462 gives us 71.14. It says round to the nearest degree, so just 71 degrees Fahrenheit to use that many according to our model. All right. So, all right, now this one, it actually looks linear even though it used a different model. So let's erase that model, and it would actually be, our equation would be y equals negative 3596.97 x plus 7338100. Okay, much better. So we'll use that one instead. We'll make sure to change that. All right, so y-intercept to this function. Well, let's do the slope first. Okay, so the slope here would be negative 3596.97 over 1. So the x is years. So as we increase in years, what's happening? Well, this negative means we're going down, so we have that many less licenses every year. Okay? So that's our slope. Then the y-intercept right here, that would mean, if we started at 2001, going backwards would be 1998, I think. So the y-intercept would be in year 1988, we had 7,338,100 marriage licenses. And that was what the y-intercept would be. Okay? So if we look, what about next year in 2019? How many would we assume? So we take that and we plug it into our equation, so we get y equals negative 3,596.97 times 2019, that was our x, plus the 7,338,100. Okay, we type that into a calculator and see what it gives to us, because we don't want to try to do that by hand. So negative 3,596.97 times 2019 plus 7,338,100. And we get 75,817.57. So that's how many marriage licenses we can assume are going to be taken out in basically Las Vegas. Okay, now it says, well, what year would 110,000 marriage licenses have been happened? Okay, so what we want to do is the same thing. Okay, but this would be the y value. So now it's like 110,000 equals negative 3,596.97x plus 7,338,100. First thing we're going to do is subtract. Oops. So I go 110,000 minus 7,338,100, which gives me a negative 7,228,100 equals negative 3,596.97x. So we divide by that negative on both sides. So then I hit divide by negative 3,596.97, and that gives me 2009. So it would make sense because it would be in between there in 2009. Okay? Now the last one. So now we're looking at the height and weight. So as your height goes up, saying your weight goes up. You can see that modeled by that equation. So slope here would be, it's 48.4 over 1. So the y would be weight here. The 1 would be feet. So for every foot you get bigger, for a person, they're saying your weight also goes up. Right? Goes up by about 48 pounds. So the y-intercept would be, taking it back down, what if we had a 0 height? What would our weight start out as? Which doesn't make a whole lot of sense in this situation, does it? But that would be at a negative 127 pounds, which you can't really have negative pounds, but in this model, that's kind of the situation we get. Okay, so now what if someone's 7 feet tall? So where would that go? So we go y equals 48.4 times 7 minus 127. And we see what that'll give us for somebody's weight. So if you're 7 feet tall, on average, according to this data, you would end up being, after I type this into the calculator, you should be around 211.8 pounds. Okay? What about someone who's 120 pounds? How much would they weigh? Well, now we work backwards, right? So I go 120 equals 48.4x minus 127. So we add 127 to both sides, giving us 247 equals 48.4x. Divide by 48.4. x equals what your height would be. So 247 divided by 48.4 would be about 5.1. Yep, about 5.1, which would be about 5 feet 1 to 2 inches, probably like 1.5 inches, something like that. Okay. All right, so there's that section. There will be kind of some stuff that I'll show you, remind you on the calculator how you can do that. But instead of using this in screenshots, I'll take a video of me actually doing it on my computer, which will probably look pretty crappy, but it'll work. So anyway, there we go.